Hello everyone, I am Khushi from BSc Chemistry Honors first year, and today our chapter is Alkanes and Cycloalkanes. Aliphatic cyclic compounds are called alicyclic compounds. These compounds are so named because they resemble aliphatic compounds in most of their properties but possess cyclic structures. However, due to cyclic nature, they differ from aliphatic compounds in some respect. Alicyclic compounds are also called carbocyclic compounds since their ring are made up of only carbon atoms. Like open chain hydrocarbons, alicyclic compounds can also be saturated or unsaturated. Saturated alicyclic compounds corresponding to alkanes or paraffins are called cycloalkanes or cycloparaffins. Those corresponding to alkenes are called cycloalkenes, while those corresponding to alkynes are called cycloalkynes. In this unit, we shall discuss the nomenclature, general method of preparation, chemical properties, and the effect of ring size on the relative stabilities of cycloalkanes. Nomenclature. The general formula of cycloalkanes is CnH2n, where n is 3, 4, 5, 6, etc. Since alkenes are represented by the same formula, therefore cycloalkanes are isomeric with alkenes. Further, since in these compounds a number of methylene units are joined together to form a ring, they are also called polymethylenes. The name of any saturated alicyclic hydrocarbon is then obtained by attaching the prefix tri, tetra, penta, hexa, etc. to the word methylene according as the number of carbon atoms in the ring are 3, 4, 5, 6, etc. respectively. In the IUPAC system, the saturated alicyclic hydrocarbons are also called cycloalkanes. The name of an individual cycloalkane is obtained by prefixing the word cyclo to the name of corresponding alkane having the same number of carbon atoms as the ring. For convenience, alicyclic compounds are usually represented by simple geometric figures, also called the polygon formula: a triangle for cyclopropane, a square for cyclobutane, a pentagon for cyclopentane, a hexagon for cyclohexane, and so on. In such representations, it is understood that each corner represents a CH2 group unless some other substituent is indicated. For example, cyclopropane, cyclobutane, cyclopentane, cyclohexane. IUPAC name of substituted cycloalkanes. The following rules are generally followed. In case of substituted cycloalkanes, the numbering of ring carbon is done in such a way that the substituent get the lowest possible numbers. The name of any substituted cycloalkane is then obtained by prefixing the name of substituent to the name of parent cycloalkane. In case there is more than one substituent, each substituent prefixed by its locant is arranged in alphabetical order before the name of parent alkane. Second, if the ring contains more or equal number of carbon atoms than the alkyl group attached to it, it is named as the derivative of cycloalkane and the alkyl group is treated as a substituent group. Otherwise, it is named as a derivative of alkane and the cycloalkyl group is considered as a substituent group. For example, 2-butyl cyclohexane, pentycyl cyclopentane, 3-cyclobutyl pentane. B point. If, however, the side that contains a multiple bond or a functional group, the alicyclic ring is treated as the substituent irrespective of the size of the ring. C. If, however, more than one alicyclic ring is attached to a single chain, the compound is named as a derivative of alkane irrespective of the number of carbon atoms in the ring or the chain. For example, dicyclopropylmethane. If a multiple, double or triple bond and some other substituent are present in the ring, the numbering is done in such a way that the carbon atom of multiple bond get lowest locants 1 and 2 and the substituent group gets the lower locants at the first point of difference. If the ring contains a multiple bond and the side chain contains a functional group, then the ring is treated as substituent and the compound is a derivative of side chain. If the ring as well as the side chain contains functional group, the compound is named as derivative of side chain or the cyclic ring according as the side chain or the ring contains the principal functional group. If a compound contains an alicyclic ring directly attached to the benzene ring, it is named as derivative of benzene, the compound having lowest state of hydrogenation. If some functional group along with other substituent groups are present in the ring, it is indicated by some appropriate prefix or suffix, and its position is indicated by numbering the carbon atoms of the ring in such a way that the functional group gets the lowest number. If an alicyclic compound contains carbon containing functional group, the carbon atoms of the functional group are not included in the parent name of alicyclic system. Therefore, for such system, the following prefix and suffix for the functional group are commonly used. Formyl prefix suffix formyl carbaldehyde, carboxylic acid, halocarbonyl carbonyl halide, alkoxycarbonyl carboxy alkyl carboxylate, carbamol carboxamide, cyanose carbonitrile. IUPAC name of bicyclic cycloalkanes. Many hydrocarbons and the derivatives contain two or more rings. The carbon atom common to both the rings are called bridgehead atoms, and each bond or chain of carbon atoms connecting both the bridgehead is called a bridge. The bridge may contain 0, 1, 2, 3, etc. carbon atoms. The bicyclic compounds are named by attaching the prefix bicyclo to the name of the hydrocarbon having the same total number of carbon atoms as in the two rings. The number of carbon atoms in each of these three bridges connecting the two bridgehead carbon atoms is indicated by Arabic numerals 0, 1, 2, 3, etc. These Arabic numerals are arranged in descending order, separated from one another by full stop and then enclosed in square brackets. The complete IUPAC name of hydrocarbon is then obtained by placing these brackets containing the Arabic numerals between the prefix bicyclo and the name of alkane. If a substituent is present, atoms of bicyclic ring are numbered. The numbering head with one of the bridgehead atoms proceed first bridgehead and it's finally completed along the shortest path. Synthesis of cycloalkanes and the derivatives. Some important general method of synthesis of cycloalkanes and the derivatives are discussed below. Cycloaddition reaction. An addition reaction between two unsaturated components leading to the formation of a cyclic product are called cycloaddition reaction. In these reactions, the pi electrons of the two components form two new pi bond. These reactions are usually designated by writing the pi electrons for the two components usually in descending order separated by a plus sign in a square bracket. For example, cycloaddition reaction. For example, cycloaddition reaction involves addition of two alkanes molecule to form a cyclobutane derivative. These reactions do not involve ionic or free radical intermediates occur in a single step via cyclic transition state in which bond making and bond breaking occur simultaneously. Such concerted reactions which occur through cyclic transition states are called pericyclic reactions. These reactions do not require any catalyst and are initiated by heat or light. The following cycloaddition reactions can be used to prepare cycloalkanes. Synthesis of cyclobutane derivatives. One of the most important methods for the synthesis of cyclobutane derivatives involves the addition of two molecules of the same or different alkenes. These reactions generally occur under photochemical conditions by a concentrate mechanism via cyclic transition state. For example, one of the most important method for the synthesis of cyclobutane derivatives involves the addition of two molecules of the same or different alkenes. These reactions generally occur under photochemical conditions by a concentrate mechanism via cyclic transition state. In case of substituted alkenes, although the addition takes place on the same face suprafacial of the alkene, yet the two molecules of the alkenes may approach each other in two different ways, giving a mixture of two products. For example, cis-2-butene or cis-trimethyl cyclobutene. Similarly, trans-2-butene or photochemical dimerization gives a mixture of two products, cis, anti-cis and or trans-trimethylene cyclobutene. It may be noted that substituted alkenes containing electron withdrawing substituents such as form cyclobutane derivatives under thermal conditions. These reactions proceed via free radical mechanism involving direct radical intermediates. Synthesis of cyclopropane derivatives. Another example of 2+2 cycloaddition reaction involves the addition of free carbenes or carbonoids, carbon-like species, to alkenes gives cyclopropane derivatives. Addition of free carbenes. Photolysis of diazomethane in the presence of propene gives methyl a free carbene, which then adds to propene to give methyl cyclopropane. Methylene itself is very reactive and hence it gives many side reactions, especially insertion reactions, which greatly reduce the yields of cyclo addition reactions. Halocarbons, on the other hand, being less reactive than methylene, do not undergo insertion reactions and hence give good yields of cyclo addition products. For example, cyclohexene 7,7 dichlorobicycloheptane 59%. Mechanism: the reaction is believed to occur by following steps. Step 1. Photolysis of diazomethane gives methylene, a carbene which is highly reactive chemical species. The methylene thus produced may be either singlet or triplet depending upon the reaction conditions employed, such as wavelength of light used, reaction phase, presence of inert gases such as argon, nitrogen, etc., and presence of photosynthesizers. Singlet methylene is used formed in the liquid phase photolysis, while triplet methylene is produced either by gas phase photolysis, especially in the presence of inert gas like N2 or AR, nitrogen or argon, or by photosensitization. Step 2. The methylene produced above adds across the double bond. According to scale theory, the mode of addition, however, depends upon the methylene produced in step 1. Singlet methylene reacts by a one-step concentrated mechanism and gives specific 6 addition products. The stereochemistry of original alkene is written in the products. In the other words, if in the original alkenes the substituent are trans, they will be trans in the product, and if they are cis, they will be cis in the product. For example, cis tubutene transition state, cis 1,2 dimethyl cyclopropane, trans tubutene singlet methane transition state 1,2 dimethyl cyclopentane. Triplet methylene, on the other hand, reacts by a two-step free radical mechanism. Similarly, we can show trans tubutene also gives the same mixture of cis and trans 1,2 dimethyl cyclopropane. Addition of carbonyl Siemens-Smith reaction. Addition of methylene to alkenes give lower yields of cyclopropane derivative, since it being extremely reactive undergoes many sides reaction, especially insertion reactions. Therefore, when it is desired to add CH2 for preparative purpose, free carbene is not used. Instead, a carbene-like species called the carbenoid is used, which generally improves the yields of the cycloaddition product by reducing the insertion reactions. On such reaction is called Simon-Smith reactions, which use diiodomethane in the presence of zinc copper couple as source of carbene like species. The addition is specifically syn occurs by concentrated mechanism as shown below. On the other hand, the reaction of trans tubutene with CH2I2 in presence of Zn couple gives trans 1,2 dimethyl cyclopropane. This reaction involves the addition of alkane or alkyne molecule called the dienophile to the conjugated diene, resulting in the formation of 6-membered ring. The Diels-Alder reaction does not require any catalyst. The two components are either heated together or heated in some solvent such as benzene, toluene, chlorobenzene, etc. The dienophilol contains an electron withdrawing group such as C double bond O, CHO, CO2H, COR, anhydride, quinone, CN, nitro, etc. The reaction can be carried out at a much lower temperature. For example, further greater the number of electron withdrawing groups, more reactive is the dienophile. Thus, in Diels-Alder reaction, malic anhydride is a useful dienophile, while tetracyanoethylene is the most reactive dienophile discovered so far. Other useful dienes are isopropene and cyclopentadiene. Stereochemistry. Diels-Alder reaction is stereospecific cis addition reaction. The stereochemistry of dienophile is retained in the product. For example, cis cyclohex 4-ene 1,2 dicarboxylic acid, malic acid 1,3 butadiene, formic acid, trans cyclo 4-ene 1,2 dicarboxylic acid. If the diene is cyclic, the two cis addition products are possible. These are called endo and the exo adducts. In the endo, adduct, the molecule of the dineophyl underneath the diene component, but in the exudate the component project away from the other. It may be noted here that the Diels reaction it is thermodynamically less stable and end product which always predominates over the most stable exoduct. Second, dehalogenation of alpha omega dihaloalkanes fronts method. This method involves the action of active metals such as zinc, sodium, unsuitable alpha omega dihaloalkane alkane having the halogen atoms on the terminal carbon atoms. This reaction may be regarded as an intramolecular Woods reaction. The reaction gives good yields for only cyclopropane alpha omega dihalides in which the two halogen atoms are further apart than the 1,6 position, do not form ring compounds but undergo Woods reaction. Dickman cyclization or condensation. Esters of alpha omega dicarboxylic acids undergo intramolecular calcium condensation called Dickman cyclization or condensation in presence of molecular sodium dust or sodium methoxide to form cyclic beta ketosters. These cyclic beta ketosters on the substituent hydrolysis or dicarboxylation yield cycloalkanes which can be converted to the corresponding into cycloalkanes by Clemson reduction. For example, cyclopentane can be synthesized from diethyl additive by following sequence of reactions. Hydrolysis of 2-carboxycyclopentane or 2-carboxycyclopentane. This is usual acidic hydrolysis of an ester to corresponding to carboxylic acid achieved by heating the esters with dilute HCl or H2SO4. Decarboxylation of 2-carboxycyclopentane cyclopentanone. Since 2-carboxycyclopentanone is a beta ketoside, it readily undergo decarboxylation on heating to give cyclopentanone. The reduction of cyclopentanone to cyclopentane. The conversion of cyclopentanone to cyclopentane is conventionally achieved by Clemson reduction. Similarly, Dickman cyclization can be used to prepare cyclohexane from diethyl pimelate. Pyrolysis of calcium or barium salt of dicarboxylic acid. Slanius method. Calcium, barium or thorium salts of dicarboxylic acid yield cycloalkanes on heating which can be readily reduced to the corresponding cycloalkanes by Clemson reduction. Planck's rule. The effect of heat on dicarboxylic acid can be summarized in form of Planck's rule, which states that dicarboxylic acids in which the two carbonyl groups are attached to the same carbon atom upon heating undergo decarboxylation to form monocarboxylic acid, and upon distillation with acetic anhydride gives cyclic ketones with the loss of one carbon atom as carbon dioxide, while 1,8 and higher decarboxylic acid remain unaffected. This rule is quite useful in determining ring size of cyclic compounds. For the purpose, a double bond is introduced in the ring by some known method. This ring is then oxidized with the help of KMnO4 to give a dicarboxylic acid, the pyrolysis of which has first to determine the size of ring. Thorpe-Ziegler reaction. This is the best method for preparation of large macrocyclic rings in good yields. It consists of treating an alpha omega dinitrile with a base such as lithium diethylamide, commonly abbreviated as LDA, lithium anthiphenamide in benzene or toluene. The dinitrile undergoes an intramolecular condensation called Thorpe reaction to form cyclic beta immonitrile, which upon hydrolysis gives the correct corresponding cyclic ketone in gold yield. The cyclic ketone can be reduced by Clemson method to give the corresponding cycloalkane. Like Dickman cyclization, this reaction also gives good yields only for 5-6 membered rings. However, by using Ziegler high dilution technique, macrocyclic rings have been prepared in good yields. In this technique, a very dilute solution of the dinitrile in the benzene is added to the solution of basic catalyst in large excess of ether. This ensures intramolecular reaction by considerably reducing the intermolecular reaction in this way yields of 95%, 86%, 60, 80 have been obtained. Yields of 9-13 membered rings are however less than 15%. Mechanism. The mechanism of this reaction is similar to Dickman condensation as it evident from the formation of aminonitrile sketched below. Damage of rearrangement. This is very useful method for expansion or contraction of alicyclic rings system through carbocatenation intermediates. The carbocatenation cations needed for this purpose are obtained by deamination of cyclic amines with nitrous acid. The initially formed carbocation may either react with a nucleophile to form the substitution product or may eliminate a proton to form an alkene. Alternatively, the initially formed carbocation may undergo rearrangement to the more stable carbocation either by ring expansion or contraction before undergoing the substitution or the elimination reaction mentioned above. Ring expansion. Dimension rearrangement involves ring expansion when the carbocation intermediate has the positive charge on the carbon atom, which is directly attached to the cyclic ring. For example, deamination of cyclobutyl methylamine gives methylene cyclobutane and cyclobutyl carbonyl as a normal P products, while cyclopentane, cyclopentanol are formed by ring expansion as shown below. Cyclobutane, carbonyl, methyl, cyclobutane, cyclopentane, cyclopentanol. Ring contraction. Dimension rearrangement involves ring contraction when the contraction intermediate has the positive charge on the alicyclic carbon atom. For example, diminishing of cyclobutylamine gives a mixture of cyclobutanol and cyclopropyl carbonyl. It may be noted here that the carbocations do not eliminate a proton to form the corresponding alkenes because cyclobutanes and methylene cyclopropane are quite useful due to single strain. Form active methylene compounds. A large number of alicyclic compounds have been synthesized by the action of active methylene compounds such as malaconic ester or acetoacetic ester on suitable dihaloalkanes. Alicyclic carboxylic ester thus formed are hydrolyzed by and decarboxylated when cycloalkanes are produced. For example, through malonic ester, sodium methoxide malonic ester, monosodium malonic ester. It may be noted here that the cyclobutane carboxylic acid thus obtained can be decarboxylated directly since it undergoes ring cleavage. However, it can be converted to cyclobutane indirectly as discussed below. This is commonly known as Perkin's method of preparation of cycloalkanes. If instead of 1,3 dibromopropane, 1,2 dibromoethane, 1,4 dibromobutane, etc. are used in above synthesis, propane, pentane, etc. can be synthesized. Journal physical properties. Cycloalkanes closely resemble their open chain analogues, that is alkanes, in their physical properties. Although their melting points, boiling points and densities are somewhat higher, this is probably due to the reason that zigzag alkanes molecules are constantly oscillating and hence can't be closely packed in the crystal lattice. On the other hand, cycloalkanes, because of their rigid ring structures, overcome this oscillation to great extent and hence are comparatively more closely packed. This closer packing results in stronger intermolecular forces, van der Waals forces of attraction, and hence cycloalkanes have higher melting points than the corresponding alkanes. In the liquid state also, the cycloalkane molecules are a little more strongly held and hence have higher boiling points than corresponding alkanes. Further, because of close packing, cycloalkanes have higher density than corresponding alkanes. The melting point, boiling point and densities of some cycloalkanes are given. Cyclopropane 154 melting point, boiling point 240, cyclohexane 279.5 melting point degree Kelvin and 354 boiling point and density is 0.778. Like alkanes, cycloalkanes are non-polar molecules and hence are soluble in non-polar solvents such as carbo, tetrachloride, petroleum, ether, etc. but are insoluble in polar solvents such as water, alcohol. The general formula of cycloalkanes suggests that they should be unsaturated and hence should resemble alkenes. However, because of their cyclic nature, they closely resemble alkenes in their chemical properties. Their similarity to alkenes is attributed to the fact that all carbon atoms in these compounds, like in alkenes, are sp3 hybridized, forming only CC यानी कि कार्बन कार्बन सिंगल बॉन्ड, कार्बन डबल बॉन्ड, pi bonds, sigma bonds, but all the cycloalkanes are not equally stable or unreactive. Only cycloalkanes from cyclopentene onwards show a degree of higher stability and are quite unreactive. As such, they are not attacked by chemical reagents, strong acids, KMnO4, LiAl4, free radical substitution reactions. Cycloalkanes undergo the typical free radical substitution reactions where 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 they are treated with halogens at 525 575 Kelvin in the dark room or at room temperature in presence of light. Addition reactions as discussed above, like alkene cyclopropane undergoes addition reaction. Some of the important addition reactions are, however, unlike alkene, cyclopropane does not add ozone and does not undergo hydroxylation with aqueous KMnO4 solution. Cyclobutane, on the other hand, is less reactive than cyclopropane and hence it does not undergo addition reaction under ordinary condition. However, on hydrogenation at high temperature, it gives N-butane. Bayer's strain theory and relative stabilities of cycloalkanes. To explain the relative stabilities of cycloalkanes and the exceptional behavior of 3 and 4 membered rings, Adolf von Baer in 1885 proposed a theory known after his name, Bayer's strain theory. The main postulate of this theory are given under below. A carbon atom bonded to 4 other carbon atoms is tetrahedral. The angle between pair of adjacent bond is tetrahedral, 109 degree 28 minute. All the carbon atoms constituting a cycloalkane molecule lie in the plane. As a result, the bond angles between any two adjacent carbon atoms are no longer equal to the tetrahedral angles of 109 degree 28 minute. They are either less or more than this angle. Any deviation or distortion from this normal tetrahedral angle imparts strain and hence instability to the resultant molecule. This strain is commonly referred to as an angle strain. The greater deviation from the normal tetrahedral angle, greater is the angle strain and hence greater is the instability of resultant molecule. The greater the stability of a ring system, more easily it is formed. The extent of angle strain introduced depends upon the size of the ring. In order to explain the relative stabilities of different cycloalkanes, let us determine the magnitude of angle strain in each of the following expression. Angle strain is equals to half 109 degree 28 minute bond angle is in the planar ring. The cyclopropane ring can be regarded as an equilateral triangle with bond angles of 60 degree. Thus implies that the angle strain in cyclopropane half 109 28 60 24 degree 44 minute. Therefore, the angle strain is cyclobutane. The positive values of angle strain indicate that the bond angles are compressed, while negative values mean expansion of bond angles from the tetrahedral angle. In the both case, the molecule will be strained. In other words, if it is the magnitude of angle strain and not its sign which determine the strain and hence the instability of the molecule. It follows the angle strain falls rapidly in going from cyclopropane to cyclopentane and then increases slowly. This means the cyclopropane with the greatest magnitude of angle strain should be less stable and hence more reactive of all the cycloalkanes, while cyclobutane with less angle strain should be a little more stable and hence less reactive than cyclopropane. Further, cyclopropane with the least amount of angle strain should be most stable of the cycloalkanes. All the predictions are in agreement with the experimental facts. On the basis of his theory, Baer predicted, of course wrongly, the cyclohexane with more angle strain should be less stable than cyclopentane. Rings larger than C7 should not exist, and if they exist, they should be highly strained and hence highly unstable. There was no way to test this prediction since rings containing 7 or more carbon atoms were not at the same time. Some important points in favor of Baer's strain theory. Reactivity of the double bond. A double bond may be regarded as a two-membered ring with a carbon-carbon bond angle of 0 degree. Reactivity of cyclopropane and cyclobutane. The comparison of heat of combustion of cycloalkanes reveals the cyclopropane and cyclobutane possess more energy per CH2 group than the corresponding straight chain alkanes. Constituently, they should be less stable than the corresponding alkanes. A fact in agreement with Bayer's strain theory. If it therefore is enabled to the belief that the tendency to undergo addition reaction through ring fusion is related to this instability. Limitations of Bayes strain theory. Some of the limitations of Bayes strain theory are as follows. On the basis of Bayes strain theory, a carbon-carbon double bond should be difficult to form since it is highly reactive and hence highly unstable. In contrast, it is known fact that a carbon-carbon double bond is easily formed by halogenation of alkyl halides, dehydration of alcohols, etc. On the basis of Bayes strain theory, cyclohexane rings having 7 or more carbon atoms should be less stable than cyclopentane, but heat of combustion data reveal the cyclopentane, cyclohexane and rings containing 7 or more carbon atoms are equally stable. Heat of combustion and relative stabilities of cycloalkanes. We know that the heat of combustion is the amount of heat evolved when 1 mole of a compound is completely burnt to form carbon dioxide and water. These furnish valuable information about the relative stabilities of organic compounds. Let us now examine whether the heat of combustion of various cycloalkanes support Bayes theory or not. A CH2 group may be expected to contribute equally to the overall heat of combustion of a compound because it yields the same product of combustion irrespective of the compound in which the CH2 group is present. But the fact that the cyclopropane and cyclobutane evolve more heat per CH2 group than the cyclopentane or cyclohexane or an alkanes means that cyclopropane and cyclobutane contains more energy per CH2 group than the cyclopentane and cyclohexane or an alkanes. In other words, cyclopropane and cyclobutane should be less stable than cyclopentane and cyclohexane or straight chain alkenes, and this is an agreement with Bayes strain theory. According to Bayes strain theory, rings larger than cyclopentane and cyclohexane should be increasingly less stable due to a corresponding increase in the magnitude of angle strain as the ring increases. Thus, if Bayes strain theory were correct, then it would be expected that the heat of combustion per CH2 group of cycloalkanes from cyclopentane onward should steadily increase as per the ring size increases. Actually, ring containing 7 to 11 carbon atoms are almost as stable as cyclopentane since they have almost the same value of heat of combustion per CH2 group, but the heat of combustion per CH2 group of cyclohexane and rings containing 12 or more carbon atoms are the same as that of N alkanes. In other words, in contrast to Bayes strain theory, cyclohexane and ring containing 12 or more carbon atoms are completely free of angle strain and hence they are stable as an alkanes. This is supported by fact that these large ring compounds such as cyclodecane, cyclopentanone, muscone have been either synthesized in laboratory or isolated from natural sources. Once these large ring compounds have been synthesized, they show little or no tendency at all to undergo the ring opening reactions characteristics of cyclopropane and cyclobutane. Mohr theory of stainless rings. As discussed above, Bayes theory could not explain reactivity stability of rings containing 5 or less carbon atoms, but failed to account for the stability of rings containing 6 or more carbon atoms. To account for the stability of 6-membered and larger rings, Mohr re-examined the models of cycloalkanes and proposed Theory of strainless rings. According to the theory, the carbon atoms of a 5-membered and smaller rings can be in a single plane as postulated by Baer, but in 6-membered and larger rings they lie in the different planes. In other words, the ring containing 5 or less carbon atoms are either planar or very nearly planar, but those of 6 or more carbon atoms are essentially non-planar or puckered. As a result of this puckering, each carbon atom retains its normal tetrahedral angle and there is negligible or no strain in the molecule. In other words, 6-membered or larger rings are strainless, and hence the name of the theory strainless rings. Further, Sachet and Mohr were able to construct the models of two puckered forms of cyclohexane called the bot and the chair forms. These forms of cyclohexane are readily inconvertible by rotation about single bond and hence represent the conformations of cyclohexane. Similarly, rings larger than 6 carbon atoms can have negligible angle strain by assuming puckered arrangement of atoms in their molecules. Now the question arises, if the large rings are stable, why are they difficult to synthesize? Baer's assumption that a compound difficult to synthesize is necessarily unstable is not correct. Actually, for ring and closer to occur, it is essential that the two ends of a carbon chain possessing the functional group must come sufficiently close together to react with each other. Evidently, larger the ring to be synthesized, larger must be the chain from which it is made, and hence less is the likelihood of the two ends of the same chain approaching each other. Under these conditions, there would be greater probability for the two different chains coupling together intermolecular condensation rather than two of the same chains undergoing a ring closure intramolecular. Thus, the difficulty encountered in the synthesis of larger membered rings in the competition between intra and intramolecular condensation with either predominating. However, recently this differentiability has overcome by carrying out the reaction in highly dilute solutions. Under these conditions, the collisions between the two different chains are minimized considerably and the ring closing although show is the case of cyclopropane and banana bonds. Cyclopropane offers an interesting case of bent C-C covalent bond. It is planar molecule and its internal bond angle theta must be 60 degree. Therefore, it is considerable deviation tetrahedral angle 109 degree 28 minute. But carbon can't be hybridized orbital oriented at an angle less than 90 degree to each other, since there are four bonds on each carbon. Therefore, the angle have to be more than 90%. In other words, in cyclopropane, the ring pi bonds can't be formed by overlap of pure atomic orbitals. To explain this ambiguity, it has been shown that the hybridization of orbitals occurs in such a way that the ring forming orbitals have a slightly greater p character than those forming the normal sigma bonds between carbon atoms in saturated molecules. This explains why the angle phi between two such orbitals of one carbon atom is in cyclopropane is 104, little less than the tetrahedral angle. Thus, the major axis of symmetry of the orbitals forming carbon-carbon single bonds in cyclopropane do not point towards one another but outwards from the molecule, with the result that the carbon-carbon single bonding molecular orbitals are not symmetrical but they are intermolecular axes but are bent, giving the appearance of bananas. It is because of the reason that the carbon-carbon bonds in cyclopropane are often referred to as bent or banana bonds. Further, due to higher p character of hybridized orbitals, there is small appreciable pi delocalization around the ring. However, delocalization occurs within the plane of the ring and not above and below the carbon framework of aromatic system. Thus, this in plane pi delocalization adds some stability to the ring. Thank you. That's all about the chapter alkanes and cycloalkanes.